In this video, I'm going to go over the solution to the water-based water balance practice problem, this time using Excel. So what I'm showing you here is the completed Excel spreadsheet, which is also available to you. And I'm going to talk through how I get all the numbers in all the cells. So the first thing to show you here are the values shown in cells B1 through 5 that I'm highlighting here. These are the data that are given by the problem: the area, the evapotranspiration rate, the precipitation rate, the stream discharge, and the change in the volume of vegetation. And notice that I've shown the units for each of those numbers in their title in column A. So for example, the area of the watershed is 3,200 square kilometers. To solve this equation, we need to write down the water balance equation. And the first equation that's shown here, the one that I just highlighted, that is the general water balance equation. It says that the change in storage over some period of time in this particular watershed, the inputs would include the precipitation, outputs would include evapotranspiration and stream flow, and we've also added an input of groundwater flow. We don't actually know whether groundwater flow is in or out, but we're going to define it as positive, so it's an input, and we're actually going to solve for it. That's the objective of this problem. And if that groundwater flow term turns out to be positive, then it is indeed an input, and if it turns out to be negative, then it will be an output of water via groundwater. So the equation, my storage equation, is written here in the equation I highlight, and we need to solve that for the groundwater flow, which I've done in the second equation. I've just rearranged the equation to solve for G. So this is the actual equation I will be solving with the spreadsheet. Now, to do this, however, you know that it's important that all of these terms have exactly the same units, dimensions and units. And notice they're not. Evapotranspiration is a rate of millimeters per year, as is precipitation. Stream flow is in volume cubic meters per second, and the change in the amount of vegetation, which is not the same as the change in the volume of water stored, is in cubic meters per year. So we have to sort of massage these numbers to create a common set of units, and we're going to use cubic meters per year. So the first thing I need to do is convert my area in square kilometers to an area in meters squared. And I'm just going to do this using the convert function in Excel. If you look at my equation up here on the top line here, I'm taking the value of the area in kilometers squared, and I'm multiplying it by the conversion factor between kilometers and meters squared. So when I do that, I end up with about 3.2 billion square meters. Now I need that area because I need to calculate the fluxes of water in to the watershed via precipitation and out of the watershed via evapotranspiration in terms of cubic meters per year. And remember, I'm given those values in terms of the rate of length per time, millimeters per year. So to convert that into cubic meters per year, I need to take that rate, convert it to meters per year, and then multiply by the area of the watershed in meters. So for example, for precipitation, if you look at my equation here, I take the rate in millimeters per year and I divide it by 1,000 to create meters per year, and then I'm going to multiply that times the value in B7, which is once again the area. So I'm taking the rate in meters per year and multiplying by the area, and I get the precipitation flux in cubic meters per year, and that's shown here in cell B8. I do exactly the same thing for evapotranspiration in cell B9. Again, converting to meters per year and multiplying by the area of the watershed. The stream flow is given in meters cubed per second, and in order to convert that to meters cubed per year, I need to multiply by the number of seconds in a year. So that consists of 3,600. I know that number is 60 seconds per minute and 60 minutes per hour. That's 60 times 60, which is 3,600 times 24, the number of hours in a day, times 365, the number of days in a year. And that gives me then in cell B10 the volume, the flux of stream flow in cubic meters per year. finally, I'm given that the change in vegetation, there's been an increase in tree growth resulting in a total vegetation change of 4.8 times 10 to the 8th cubic meters of vegetation. And we're also told that that vegetation is about 50% water. So to get the change in the volume of water stored in that vegetation, I take the volume of the vegetation and I multiply by 0.5, or I divide it by 2. And so I can do that in my head, right? 4.8 times 10 to the 8th, half of that is 2.4 times 10 to the 8th, and that represents the change in the volume of water stored in the aquifer during that year. So now I have all of these terms here. These are all I'll highlight these just to show you what they are. These are all now terms that I need in terms of meters cubed per year. These are all the terms in this equation here, and I merely need to plug into this equation to solve for the groundwater flow in cubic meters per year. So this is exactly what that equation says. It takes the change in storage minus the precipitation flux plus the evapotranspiration flux plus the stream flow flux, and when I do that and solve that equation, I end up with the answer, which is 9.6 times 10 to the 7th cubic meters per year of groundwater flow. Once again, because that's positive and I've defined positive as inflows, this tells me that groundwater is a net inflow to the watershed. So my answer is groundwater is flowing into the watershed at a rate of 9.7 times 10 to the 7th cubic meters per year. Those are the two answers that I've shown in blue. I've also done this equation by hand, and if you want to look at it in more detail and written out in terms of the conversions, you should look at that solution as well.